Hello, everyone. We are going to talk about exponential functions today. So, an exponential function is a function of the form f of x equals a b to the x, where b is a positive number, it's not 1, and a is not 0. While linear functions are defined by a constant rate of change, exponential functions experience what's known as a common ratio. All right, so I'm gonna fix this e because it's bugging me here. There we go. So do these tables here represent exponential or linear functions? So notice how in all of these my x's are increasing by the same amount. They're increasing by 1. So since they're all increasing by 1 here, I can go ahead and just look at the change in the y values to figure out whether these are exponential, changing by multiplying or dividing by the same number, or linear, adding and subtracting by the same number. So let's see, 5 to 2, that's like going down by subtracting 3, 2 to negative 1, minus 3, negative 1, negative 4, minus 3. So that makes, since we're subtracting the same number over and over, this is going to be linear. Over here, from 2 to 6, and then from 6 to 18, and from 18 to 54, what we're doing here is we're multiplying by 3 every time. And so since we're multiplying by the same number, this is going to be exponential. All right. So let's go ahead and write some functions here. So an exponential function, so it's going to be exponential, and it's going to have a base of 4 and a y-intercept of negative 2. So we have to talk about what this y-intercept means for exponential functions. So you'll recall a y-intercept, right, is the y-coordinate where the graph crosses the y-axis. So our x is 0. So if we were to have, let's call this y sub 0, our function that looks like b to the x, if I replace x with 0, we have y equals a to the b to the 0th power. The b to the 0th power is 1. So this gives us that y is just a. So our y-intercept, a, is always our y-intercept here in an exponential function. All right, so if I were to write this exponential function here, let's call it f of x. It is a function after all. So that means that negative 2 goes in the spot for a as my y-intercept. That has a base of 4. So we're going to have f of x is equal to negative 2 times 4 to the x. All right, now we're going to look at this function here, f of x, and it contains the points 1, 15, and 3, 375. So one way I like to think about this is with a table. So I'm going to need to know that y-intercept, right, 0, my starting amount. Then I know the point's 115. Don't know what's happening at 2. And I know at 3, I have 375. So I know that whatever my base is, to get from 15 to whatever this y value is, I've multiplied by my base. And then I've multiplied by my base one more time to get from that number to 375. So what I'll do is I'll set up this equation here. 15b squared is going to get me 375. And now we can solve, right? We can think about what's happening here, right? So if I divide both sides by 15, I'm going to get b squared is equal to 25. You'll recall, right, that 5 squared is 25. So this tells me that my base is going to be 5 for this equation. So we can use that to kind of work backwards to find our y-intercept. So, because whatever this a value is, right, I multiply that by my base one time, and that's how I got 15. So if we do 15 divided by, hold on, that ended up super ugly. So a here is going to be 15 divided by 5. Or 3. So this function, we also called f of x, it's going to look like 3 times 5 to the x. All right. So now we are going to think about these equations look like graphically. So graphing y equals a b to the x. So there's some key features of graphs of exponential functions that we want to think about. So when our base is a proper fraction between 0 and 1, the graph is going to decrease from left to right. And so it's not going to look like the graph that I have shown here, but it's actually going to look like this graph here to the right, where it's decreasing from left to right. So this line, right, this one happens when b is a proper fraction. Now when b is greater than 1, the graph increases from left to right. So this one here, this is what it looks like if it has a base greater than 1. And then this part we talked about on the front, the y-intercept is a. Now a couple other things to consider here are the domain and range. The domain and range of both of these functions are the same, whether the decreasing or the increasing one. So if you look, domain range is a set of all possible x values that our graph takes on, and it keeps increasing forever and ever and ever to the left and to the right, or it keeps on going to the left and to the right forever and ever. So that is going to be all real numbers. Or your teacher may use this symbol, the blackboard bold, for R. Now when we think about this range, I've highlighted this y-axis here, or this x-axis here, where y is 0. And what's going on here is that our graph is getting closer and closer and closer and closer to it, but it's never going to actually touch that line, y equals 0. So that means that we consider our range, we're not going to include it. So we'll say our y's are all strictly greater than 0, but not equal to 0. All right. So for graphing these, we're just going to look at some basic examples, and we're going to graph using a table. So all we have to do here, right, to graph using the table is plug in our values for x. So for example, here this would be 3 to the negative second. And we know with properties of exponents, that can become 1 over 3 squared, or 1/9, so on. So we can fill in this next one. This would be 1/3. When we plug in 0, we'll just get out 1, 3, and 9. So now I can plot those points here. So -2 is super, super small, really close really close to negative, or to 0, but not 0. Then at -1, a little bit bigger. 0 is at 1, 1, 3, 2, 9, and then we can connect the dots, making sure your graph kind of swoops up like that. It's getting closer and closer and closer to the x-axis, but it's not touching. And so next we have this one. So 1/2 to the negative second, right? We're going to have the reciprocal, which means that this is going to become 1 over 1/2, which will become 2 squared, which will be 4. This will just be 2, 1, 1/2, and 1/4. So you can see here how this is actually going to get smaller from left to right. So at -2, we're up at 4, and then -2. And you can see how we get kind of that swoop curve nature from this graph. It's definitely not a straight line like we've been seeing with linear functions, right? But from point to point, how the y values are changing, right? It's not relative to each other. It's not that constant rate of change. All right, guys, there you have it. Exponential functions, just a little taste before we get into some modeling.